Hello everyone, welcome back again to Beyond Tutorials. In this video, we are talking about Chapter 7, Refrigeration Cycles. The term refrigeration means cooling a space, substance, or system to lower and or maintain its temperature below the ambient one, while the removed heat is rejected at a higher temperature. In other words, refrigeration is artificial or the human-made cooling. So in refrigeration cycles, it tackles here about heat rejection from heat to cooling. So we have here the refrigeration cycle. It first comes with a compressor, from compressor to hot gas to the condenser. So when the condenser passes the hot liquid to expansion valve, and from expansion valve passes cold refrigerant to evaporator, and evaporator passes gas to compressor, and the cycles goes on. So for better understanding, let's solve some problems regarding with this. So example number 1. A Brayton cycle with an ideal regenerator has an inlet at 290 Kelvin as our temperature 1 and 90 kilopascal as our pressure 1 with the highest pressure, and temperature as 1170 kilopascal as our pressure at state 2 and 1700 Kelvin as our temperature at state 3. Find the specific heat transfer and the cycle of efficiency using cold air properties. So first we need to list down all the given. We have the T1 as was mentioned here in the statement, 290 kilopascal, pressure which is 90 kilopascal, pressure at state 2 1170 kilopascal. Since P2 is equal to P3, we have also same 1170 kilopascal, and at state 4 90 kilopascal, and temperature at state 3 which is 1700 Kelvin. So at 90 kilopascal, the specific heat is 1.004 kilojoule per kilogram degree Kelvin, and the proportionality which is 1.4 as the proportionality constant. So by solving the temperature at state 2, we can use this equation. Temperature 1 at state 1 multiplied by the pressure at state 2 over the pressure at state 1 raised to proportionality K constant minus 1 over the proportionality K. So by plugging all the values that we have here, 290 Kelvin multiplied by 1170 kilopascal of 90 kilopascal raised to 1.4 as our proportionality K constant minus 1 over 1.4, and by plugging this into our calculator we get 603.5 Kelvin. So by finding the temperature at state 4, we use temperature at state 3 multiplied by the pressure at state 3 over the pressure at state 4 raised to proportionality K constant minus 1 over K. So by plugging all the values and the given values into our equation, we get 1700 Kelvin multiplied by 1170 kilopascal at pressure 3 over 90 raised to 1.4 minus 1 over 1.4, and we get the temperature at state 4 which is 817 Kelvin. So by finding the specific heat transfer, we have this equation, the specific heat multiplied by temperature at state 3 minus the temperature at state 4. So by plugging the values in our equation, equals 1.004 kilojoule per kilogram degree Kelvin as our CP, or the specific heat, which is the specific heat, multiplied by 1700 as our temperature at state 3 minus 817 Kelvin as our temperature at state 4. So we can get the specific heat transfer, which is 886.5 kilojoule per kilogram. So for finding the cycle efficiency, we have this equation 1 minus the specific heat multiplied by the temperature at state 2 minus temperature at state 1 over the specific heat multiplied by the temperature at state 3 minus the temperature at state 4. So by plugging all the values, we have 1 minus 1.004 as our specific heat multiplied by 603.5 minus 290 over 1.044.1700 minus 817 Kelvin, and we have, by plugging this into our calculator, we have the cycle efficiency of 0.64 or 64%.